Welcome, chemistry students. You are welcome to the second semester chemistry course, General and Inorganic Chemistry. Unit 5 in this course is on acids and bases. Chapter 5.3 in Unit 5 is on types of salts and salt hydrolysis. The instructor for this chapter is Dr. P. Sharada, Selection Grade Lecturer in Chemistry, St. Joseph's College for Women, Autonomous, Visakhapatnam. Learning outcomes. By the end of this chapter, the learner should be able to define pH, pKa and pKb and also understand their utility, classify salts into 4 types based on the strength of the acid and base, sketch the mechanistic pathway of cationic and anionic hydrolysis, and also predict the nature of the resultant salt solution. Contents. The contents of this chapter are definition of pH, pKa and pKb, ionic product of water, salt hydrolysis and hydrolysis of different types of salts. Now we go into the lesson and look at the first part of the chapter, which is on definition of pH, pKa and pKb. What is pH? pH is the negative logarithm of hydrogen ion concentration. The pH scale extends from 0 to 14, though pH of less than 0 and greater than 14 are also possible. pH is a scale used to denote acidity or basicity of an aqueous or other liquid solutions, non-aqueous solutions also. It is the molar hydronium ion or hydrogen ion concentration which is expressed on the pH scale. This scale ranges from 0 to 7 and from 7 to 14. pH is logarithmic, negative logarithm of hydrogen ion concentration. So, pH is logarithmic and inversely indicates the activity of hydrogen ion in solution. Activity of hydrogen ions in solution. But in very dilute solutions of less than 0.01 molar concentration, activity can be taken as molarity, or conversely molarity is equal to activity. So, though pH is logarithmic and inversely indicates the activity of hydrogen ion concentration in solution, activity can be equated to molarity in very dilute solutions whose concentration is less than 0.01 molar. pH is equal to minus log activity of hydrogen ion concentration, which is equal to minus log molarity of hydrogen ion concentration, where H plus in square brackets is the equilibrium molar concentration of hydrogen ions. It is a measure of relative amounts of free hydrogen or hydronium, both mean the same, free hydrogen and hydroxyl ions in solution. Pure water has a hydrogen ion concentration of 10 to the power of minus 7. At room temperature, less than 7 pH indicates acidic nature of the particular solution, greater than 7 pH indicates basic nature, and exactly 7 indicates the neutral nature of the solution. You can see here number of substances that we come across in our day-to-day life are shown, and their pH is also mentioned. You can see here stomach acid pH is 1. battery acid pH is 0. Come to this side, your drain cleaner, soap, their pH is alkaline or basic. Drain cleaner pH is 14, soap pH is 12. So these substances, coffee has a pH of 5. This is the scale from acidic 0 to basic 14. But remember, pH of less than 0 as well as greater than 14 is also possible. Next, let us see what is pKa. Here we have indicated the hydrogen, the acid HX in water. Acid HX in water dissociates to form H3O plus and X minus. So if you want, we said at equilibrium, we said equilibrium concentration. Supposing we presume that this reaction is now in equilibrium condition. So the equilibrium constant for this reaction is given by molar concentration of H3O plus into molar concentration of X minus divided by molar concentration of HX. So for the acid dissociation constant, because you are taking an acid HX in water, we denote this K as Ka with a subscript A. So Ka stands for acid dissociation constant. So acid dissociation constant is measured after attainment of equilibrium condition, wherein in the numerator you take the concentration of H plus ion or H3O plus ion along with the corresponding anion, and in the denominator we take the concentration of the undissociated acid. So just by looking at this equation, you can make out that Ka value will be very high if all HX is dissociated to form H3O plus and X minus. So higher the Ka value, stronger is the acid. That is, the more the HX undergoes dissociation, the more will be the Ka value. Why? Because you have HX in the denominator. So at the equilibrium point, concentration of HX will be very low and concentration of H3O plus will be very high. So acid dissociation constant is directly proportional to the strength of the acid, or it is directly proportional to the H plus ion concentration. Ka is a measure of the degree of dissociation of the acid. At temperature T, acid dissociation constant Ka is directly proportional to the strength of the acid HX. Stronger the acid, higher will be the Ka value. And also, what is pKa? Just as pH, pKa is the negative logarithm. You can see here, pKa is the negative logarithm of the hydrogen of the Ka value. That is to say, Ka is directly proportional to the acid concentration or the H plus ion concentration, but pKa will be inversely proportional. Why? Because you are taking the negative logarithm of Ka. So lower the value of pKa, stronger is the acid. Lower the value of pKa, stronger is the acid. We have given here a number of acids. You can see here hydrochloric acid is having a very high Ka value but a very low pKa value. And here you can see at the bottom acetic acid is having very low Ka value but a very high pKa value. So higher the pKa value, weaker is the acid. Lower the pKa value, stronger is the acid. So what is pKa? pKa is the negative logarithm of acid dissociation constant Ka. Ka directly measures the hydrogen ion concentration in the solution. Higher the value of Ka, stronger is the acid. So lower the value of pKa, stronger will be the acid. Why? Because pKa is the negative logarithm of Ka. Same is the case with pKb. Now let us see what is pKb. You can see here a base is shown. The base is shown as MOH. M stands for metal. So MOH aqueous will form M plus and OH minus. So equilibrium condition is attained. We presume that the reaction is at equilibrium condition. So you measure the base dissociation constant Kb is expressed as molar concentration of metal ion M plus into molar concentration of OH minus divided by MOH, molar concentration of MOH. You can see here M plus and OH minus are on the product side. MOH is on the reactant side. So, when will the Kb value be high? Kb value will be high when the numerator is high and the denominator is low. That's common sense. So, the MOH concentration should be low. When will the MOH concentration be low at equilibrium? When most of MOH has undergone dissociation to form M plus and OH minus. So, base dissociation constant Kb directly measures the concentration of the OH minus ion, and it is directly proportional. Higher the value of Kb, stronger is the base. So, it is directly proportional to the strength of the base MOH. What is pKb? Just like pKa, you know, pKb is also the negative logarithm of Kb. pKb is the negative logarithm of Kb. So, lower the value of pKb, stronger is the base. Lower the value of pKb, stronger is the base. For example, you know, lithium hydroxide is a very strong base. It is having a very low pKb value of minus 0.36. A high Kb value and a low pKb value will indicate a strong base. Conversely, a low Kb value and a high pKb value will indicate a weak base. Now, let us move on to the next part of the lesson, that is ionic product of water. So, what is ionic product of water? Ionic product of water is Kw, you know, it is the product of, suppose you presume that one water molecule is acting as a base, another water molecule is acting as an acid. So, the two water molecules react between themselves and you get H3O plus as the conjugate acid of the base H2O and OH minus as the conjugate base of the acid H2O, because we know very well in our previous video we have seen that H2O can act both as an acid as well as a base. So, we presume here that one molecule of H2O is an acid, another molecule of H2O is a base, and between themselves they form H3O plus as the conjugate acid and OH minus as the conjugate base. So, if you presume that the equilibrium condition has been attained, so equilibrium constant, also called as the ionization constant K, is equal to molar concentration of H3O plus into molar concentration of OH minus divided by H2O. Since the concentration of H2O remains constant because of very high molarity, it is the medium in which it is the only molecule or the medium in which the process is occurring, its concentration is very high, no perceivable change occurs. So, H2O concentration is taken as unity and concentration of H2O is omitted in the denominator because water is a pure liquid and its concentration remains constant. Therefore, Kw, you removed water from the denominator. Now, K is written as Kw. Kw is equal to H3O plus into OH minus. This Kw is what is called as the ionic product of water. Kw is the ionic product of water, and this ionic product of water is dependent on temperature T. So, at 298 Kelvin, that is room temperature, H3O plus concentration, H3O plus is the hydronium ion concentration. So, at room temperature, the hydronium ion concentration is 1.0 into 10 to the power of minus 7 molar, which is also equal to OH minus ion concentration. Why? Because for every 1 mole of H3O plus you are also getting 1 mole of OH minus. So, for every 1 mole of H3O plus, you are also getting 1 mole of OH minus. So, the total, ionic product of water Kw is the product of the two, molar concentration of H3O plus into molar concentration of OH minus. So that is the reason why we take 1.0 into 10 to the power of minus 7 square. You can see here 1.0 into 10 to the power of minus 7 whole square, which is equal to 1.1 into 10 to the power of minus 14 molar square, because it's a molar concentration, M is the molar concentration. So 1 into 10 to the power of minus 14 molar square is the ionic product of water at room temperature. At room temperature, Kw is equal to 1.0 into 10 to the power of minus 14 m square. If any particular solution, if the concentration of H3O plus is greater than that of OH minus, such solutions are acidic. Why we got this 1.0 into 10 to the power of minus 14? Because it is pure water, no other substance is there. For every 1 mole of H3O plus, you are getting 1 mole of OH minus also. So both their concentrations are equal. But if due to the presence of some substance, if the concentration of H3O plus is greater than the concentration of OH minus, such a solution is acidic in nature. If the concentration of H3O plus is less than that of OH minus, such a solution will be basic in nature. And if H3O plus concentration is equal to OH minus concentration, such a solution is neutral. That's the case we have discussed just now to evolve the value of ionic product of water. So what is ionic product of water? Ionic product of water is simply the product of molar concentration of H3O plus and molar concentration of OH minus in pure water at 298 degree Kelvin. Now let us move on to the next part of the chapter, that is about hydrolysis of salts. How is a salt formed? A salt is formed by the combination of an acid and a base. This we have been learning right from the beginning. Acid AH plus base BOH together will form AB salt along with water. So acid plus base forms salt plus water. What is hydrolysis? Lysis is to break. Lysis means break. Salt hydrolysis means breaking the salt, breaking the salt. The salt when put in water, salt will break into anion and cation. Either the anion or the cation or both of them will interact with water and break the water molecule into H plus and OH minus. You understand? So formation of salt is between acid and base. But when this salt is put in water, it undergoes hydrolysis. You can see here, Ba is the salt. You put it in water and you got the acid and the base back. AH, that is Ha and BOH. Ha is the acid, BOH is the base. Depending upon the relative strengths of the acid and the base, you will determine whether the resultant solution is acidic or basic in nature. You can see here, lysis means break. The breakdown of salts, which are strong electrolytes, into anions and cations. First, as soon as you put the salt in water, it will break to form the anion and cation. These anions and cations now interact with water. The interaction of anion or cation or both with water is called salt hydrolysis. And because of salt hydrolysis, pH of water or pH of the resultant solution is affected. Because of salt hydrolysis, pH will be affected. If salt hydrolysis produces strong acid, which is fully ionized, and a weak base, which is partly ionized, you get the resultant solution as an acidic solution. If salt hydrolysis produces a weak acid, that is weakly ionized acid, and a fully ionized base, The resultant solution will be basic in nature. So when will the salt hydrolysis lead to an acidic solution? An acidic solution is produced when the strong acid means HA is the acid, BOH is the base. HA is very strong. So the strong acid is fully ionized to form A minus and H plus. You can see here it is fully ionized to form the A minus and H plus. But the BOH is intact. It is staying as BOH only. So it is called as cationic hydrolysis, which will produce acidic solution, which will result in the formation of acidic solution. So cationic hydrolysis will lead to the formation. You know how from where you got the cation? Cation came from the B plus. BOH is there. BOH will produce B plus and OH minus. That B plus will interact with water. You can see here, B plus will interact with water to form BOH, and because of formation of BOH, which is weakly ionized, the H plus concentration will increase and the resultant solution will be acidic in nature. So how do you get acidic solution? Due to cationic hydrolysis. Now you can see here cationic and anionic. What is anionic hydrolysis? So anionic hydrolysis means, you can see here, B plus and A minus is the salt. Our salt we thought is Ba. So B plus and A minus plus water, you got the acid HA, which is weakly ionized, and the base B plus and OH minus, which is fully ionized. The A minus, the A minus will react with water to form the unionized or weakly ionized HA along with the release of OH minus. So the OH minus concentration in the solution will be higher, and because of higher concentration of OH minus, the resultant solution will be basic in nature. If salt hydrolysis produces a strong base which is fully ionized and a weak acid which is partly ionized, this hydrolysis is called anionic hydrolysis, and anionic hydrolysis leads to the formation of a basic solution. Water reacts with anions of salt. You can see here, the anion is reacting with water. Water is reacting with what? The anion obtained from the salt. So cationic hydrolysis produces acidic solutions, and the resultant solution will have H3O plus concentration greater than OH minus, and anionic hydrolysis will produce basic solution. Here H3O plus concentration is less than OH minus ion concentration. Now let us see the different types of solutions that are obtained due to salt hydrolysis. There can be 4 types of salts, and due to the hydrolysis of such salts, what kind of solutions we get? Let us see. So what is salt hydrolysis? So far we have learnt salt hydrolysis is the reaction of the cation or anion of the salt with water to produce either acidic or basic solution. On the basis of relative strength of acid and base produced due to hydrolysis, salts are classified into 4 types. Salts can be of 4 types. Salt of a strong acid, strong base, strong acid, weak base, weak acid, strong base, and weak acid, weak base. We have also given 4 different examples. In the next slide, we will learn about the different types of salts and the solutions that are obtained due to their hydrolysis. The nature of the solutions. Will they be acidic? Will they be basic or neutral? Now let us see. Salt of a strong acid and a strong base. Right from our childhood we know this salt, NaCl. NaCl is the salt of a strong acid. What is that strong acid? HCl. What is the strong base? NaOH. So HCl and NaOH combine to form NaCl and water. Here anions and cations. So what anion you will get from NaCl? Cl minus. What cation you will get from NaCl? Na plus. When you put NaCl in water, you will get Cl minus ions and Na plus ions, but mind you, they are only hydrated. They don't cause hydrolysis. they don't cause hydrolysis or they don't undergo hydrolysis. They will only cause, they will only get hydrated. For example, you can see here Cl minus is surrounded by the positive H plus ends, because water is a polar solvent. Oxygen will get partial negative charge. The blue balls are the hydrogens. Hydrogens will get the partial positive charge. So the negatively charged chloride ion is surrounded by the partial positive charge bearing H plus ions. If you see the sodium ion here, sodium ion is surrounded by the partial negative charge bearing oxygens of water. So both chloride and Na plus are only hydrated. They don't undergo hydrolysis. So the resultant solutions are neutral. So the solution of a salt formed from a strong acid and a strong base is neutral. So the solution of a salt formed from a strong acid and a strong base is neutral. That is the first case. Now let us see the second case. The second case is salts of strong acid and weak base. Strong acid, weak base. Example we have taken as ammonium chloride. We know very well that ammonium chloride salt is formed from, see look here, ammonium chloride is formed from which acid and which base? HCl is the acid. Ammonium hydroxide is the base. Together they react and form ammonium chloride. So ammonium chloride when kept in water will ionize to form ammonium ions and chloride ions. Now ammonium ion will react with water and form ammonium hydroxide. You can see here ammonium will react with water. You can see here water is there. So ammonium will react with water to form ammonium hydroxide, but ammonium hydroxide is a very weak base. It is having a very low Kb value. Kb value is the base dissociation constant value, which is only 1.77 into 10 to the power of minus 5. So it doesn't undergo any breakage. Ammonium hydroxide is formed, but it is not ionized. That means OH minus ions are locked. OH minus ions are nicely locked. So what happens when ammonium is reacting with H2O? It is forming ammonium hydroxide and it is also leading to the release of H plus. So H plus will start getting accumulated. Ammonium hydroxide is not ionized. Ammonium hydroxide is not breaking. It is not releasing OH minus. But H plus ions are adding up. So gradually H3O plus ion concentration will be greater than OH minus ion concentration. So the solution will be acidic in nature. So what did you understand? Solutions of salts of strong acid and weak base will be acidic because H3O plus ion concentration is greater than OH minus ion concentration. Now let us look at the other two types of salts. The third case is salts of weak acid and strong base. The previous case is strong acid, weak base. Now it is salts of weak acid, strong base. Example is sodium acetate, CH3COO Na. So how is this sodium acetate formed? By the combination of acetic acid and NaOH. Acetic acid is a very weak acid. In the previous slides we have seen. The acid dissociation constant of acetic acid is very low. It is at the bottom of the table. And sodium hydroxide is at the top. It's a very strong base. So CH3COO Na is ionized to form Na plus ions and CH3COO minus ions. CH3COO minus ions will react with water. They form acetic acid and release OH minus. Because acetic acid is not ionized, because acetic acid's dissociation constant is very low, 1.8 into 10 to the power of minus 5, very low. So it doesn't undergo ionization, it doesn't release H plus ions, it will release very few H plus ions. So OH minus ion concentration will be much higher than the H plus ion concentration, so automatically the resultant solution is basic in nature. The resultant solution is basic in nature. So solutions of salts of weak acid and strong base are basic in nature. Now let us go to the last case and the last part of the video, that is salts of weak acid and weak base. When the acid is weak and the base is also weak, the solution, both acid and base are weakly ionized. Because they are not fully ionized, whether the resultant solution will be acidic or basic is controlled by this formula, which is 7 plus pKa minus pKb by 2, which is pKa is the logarithmic, negative logarithmic value of acid dissociation constant. pKb is that of the base. So if pKa minus pKb value is positive, solution is basic. If it is negative, the solution will be acidic. If it is 0, the solution will be equal to neutral. So whether you take solution of salt of a strong acid and a strong base, or the solution of salt of a weak acid and weak base, most likely both solutions are, the first one is for sure neutral, the second one is also almost neutral. It will be little basic or little acidic depending upon the values of pKa and pKb. So we end this chapter just by recollecting what we have learnt in this particular chapter. What did we learn? We have learnt that pH is the negative logarithm of H plus ion concentration. It is actually H plus ion activity, but in very dilute solutions, activity is equal to molar concentration. So minus log H plus ion concentration. pH scale is used to denote acidity or basicity of aqueous solutions and other liquids. Magnitude of pKa and pKb is inversely proportional to the strength of the acid and base respectively. Ka and Kb are directly proportional, but pKa and pKb are inversely proportional. Salts are strong electrolytes and they readily ionize into cations and anions in water. They are highly ionic. So the moment you put a salt in water, they will ionize to form cations and anions. Cations and anions of salt interact with water and undergo hydrolysis. Finally, pH of the resultant solution can change due to salt hydrolysis. So we have seen salt of a solution of a salt of a strong acid and a strong base is neutral. Solution of a salt of a strong acid and weak base is acidic. Solution of a salt of weak acid and strong base is basic. So that is how the resultant solutions nature will differ from or will depend on the type of the salt. So thank you. All images are adopted from open web pages. Thank you.